This video is working on velocity time graphs, and we're going to be reviewing the velocity time graph that I provided you in class, and we're going to go through the 4 questions that were posted on Google Classroom. First question is dealing with what is the acceleration of the object during the first 0.8 seconds? Well, the first thing you have to realize when you're looking at this particular velocity time graph is that this is a linear relationship. So it doesn't matter where you calculate the slope along this line, it's all going to be the same. So I know I've asked for the first 0.08 seconds, but as long as you calculate the slope anywhere along this line, you're fine. So I always try to pick points I know fall in an intersection between 2 increments, so I can get the best read on what types of numbers I'm going to be using. So numbers that I used, I was going to start off at my 0.2, and then that corresponding number is negative 73. So I am starting down at this point here, and then I'm going to be moving on to about the 0.6 mark, and that corresponding number is about negative 39. So using those 2 numbers and knowing that the slope of this line equals acceleration, and that's a vector quantity, so that's acceleration with a direction. So I am going to use these numbers now to calculate my answer. So acceleration is going to equal v2 minus v1 divided by t2 minus t1. And so again, I'm looking at my change in velocity. So in this case, I have negative 73 subtract negative 39.0, and that should be a 0.0 as well, sorry. And that is then divided by 0.60 subtract 0.20. That gives me a negative 34.0 divided by 0.4. And that gives me with, or ends up with a, that gives me 85 meters per second squared. Now it's a negative 85 meters per second squared, 2 significant digits, because that's what my count is on my denominator. Now I have to put meaning to that negative 85, and so I want to make sure I put a direction with that. So there's 2 ways I can write this. I can say this is negative 85 meters per second squared, and then I can use what's labeled on the axis. I can say that is up, which means I'm really going down, or I can write 85 meters per second squared, and I can even put a little arrow pointing down indicating my direction. So again, the acceleration rate does have a direction in this case. The acceleration rate is dictated by that negative or positive. So when you're doing your calculations, you do want to make sure you're paying attention to that, whether your answer is negative or positive, because that does dictate the direction. And again, if you look at the object itself, it is slowing down and eventually crosses that 0 point. So that's it for number 1. The second question looks at whether the object is turning around and then justified. Again, the most important part about this particular question is just the justification process and just explaining the detail needed in order to get full marks for this type of question. So in short, I mean, the answer is yes, it does turn around, and we know it turns around because it crosses this x-axis, which is the 0 point. So all the way from its initial velocity, which would be v1. As it's moving, it progressively gets slower and slower and slower until it reaches that point where it crosses the axis, and that means it is now going zero velocity. Once it passes that point, then it's going to increase in velocity. That is a classic sign that you want to look for. As soon as it crosses that x-axis on a velocity time graph, we switch from slowing down, coming to a stop at the x-axis, and then speeding up afterwards. And that's what you have to do every time an object turns around. Now, that time that it actually stops can be very, 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 very small, but it still exists. Any object that turns around must slow down, stop, and then turn around. Now, to justify, I've just provided a slide to kind of summarize some key things you should include in your explanation. The first thing is, yes, the object does turn around. Right? So you do want to state what the actual answer is. Then the next thing is dealing with looking at the line of best fit. And you're looking at that where it crosses that x-axis. So it does indicate two changes, and those two changes are key to your explanation. First one, where it meets that x-axis, we know that it comes to a stop, and that's one of the key components of an object turning around. We know it has to come to a stop, so you need to justify that by saying that that x-axis is representing the point where the object is motionless or has come to a complete stop. Now, that object could keep going the same direction and stay in that same quadrant. So it's just saying it just comes to a stop at that x-axis doesn't mean that it necessarily has turned around. So that's why you have to bring in the second point, that the line of best fit continues past the x-axis and goes into the positive quadrant, which indicates that the object has changed direction. And that's the other key component, that you've moved from the negative to the positive quadrant. The y-axis has labeled the negative quadrant as down and the positive quadrant as moving up. And that you have to go back to that label of that y-axis, explain what the meaning of that y-axis is, and the meaning and how that's related to your your positive quadrant and your negative quadrant. And then that would completely justify your answer. So again, you want to state what the answer is. You want to state that the object comes to a stop, and that's justified by the line actually touching the x-axis. And then you want to explain what's happening in the negative quadrant versus the positive quadrant, what is the meaning of that, and how that's related to your y-axis. Third question is dealing with what is the overall displacement of the object. And again, the key there is we're talking about displacement. So now we want to know, where are we in relation to that reference point? If I asked about distance, yeah, I would want to know, it doesn't matter what direction they're going, I want to know what their total distance or the total length of travel was. Displacement is different, and so then you have to be, you have to think about, okay, what time have they moved up, what time have they moved down, and how far have they gone during those time periods. Now, in a question like this, again, you want to identify different components of the graph. So the first area is this one, and in that section we know that the object is moving up because that is the positive quadrant. That's what my y-axis is indicating. Everything under here, so from the 0 point all the way down, so in that area we are going down, right? So we're going two opposite directions, and so we really want to find the net displacement of those distances. Now, the easiest way to approach a question like this is to find where there is a uniform acceleration, because when you find a uniform acceleration, then you can just use a kinematic equation to solve the displacement for that section. So that is found with this entire line. You can treat that as a constant acceleration because it's a linear relationship. And because you can do that, you can put it into your displacement formula, which is just the rearrangement of your velocity formula. So you're really taking your velocity, so VAV, and we know that equals displacement over the change in time. If I rearrange that and I look at my displacement, and that's going to equal my velocity times time. Now, I need to expand that because I have a V1 and a V2. So I'm going to take my displacement, and this is really expanded, V1, sorry, plus V2 divided by 2, that's average, times time. So I'm going to take a look at that, and I know I can pick out my V1 here, and then I can go at the very end of this linear section and figure out my V2. And then I know my time frame during that that section of line is going to be 1.4 seconds. So I'm going to plug that information in. So I know that my V1, is negative 90, because that's where it crosses the y-axis, 0.0, plus 29.0, and then I'm going to divide that by 2. The 2 doesn't factor into significant digits. And then I'm going to multiply that by my time period, which is going to be 1.4. So I can do that calculation, and what that calculation will give me is my displacement during that period of time that we are going a constant acceleration. Alright, so after that calculation, you get a displacement of negative 42.7 meters up, which means that I've really moved 42.7 meters down. So again, we want to make sure we keep that negative in our calculations, just as a reminder of what direction we're really going during that phase of the motion. The last bit of the motion is now dealing with the section that is in the linear portion. So, not the linear, but the constant velocity portion. So I'm just going to erase a little bit of my calculations that I have there. So what we're dealing with here is this section underneath the line. So again, that's the area, so that's really length times width. And so what we're going to calculate there is the displacement of that section. So again, we know that displacement is going to equal VAV times time. Now, we don't need to expand on that because it's a constant velocity in that section. So we know that that constant velocity is 29.0, and we're going to multiply that by the time frame that they went, that 29.0. So that was 0.40 seconds. So then we know that displacement is going to equal 10.29 2.95 meters. Again, that's positive, so then we know that that is up. So now we have two different directions. We have positive 10.295 meters up, and then we also have our negative displacement, which was 42.7 meters up, which really means we're going down. So then you're just finding the sum of those two totals. So again, you're going to sum those. So we got our 42.7, and then we're going to add our 10.295. Again, those are going opposite directions. That's why we have a negative at the 42 and then a positive at the 10. So then our overall displacement ends up being negative 32.4 meters. That is up. Or you can write that as 32.4 meters down. Either way is acceptable. But again, the key to that question is understanding where there is a linear relationship, and that linear relationship shows you that it is a uniform acceleration. That's what allows you to use a kinematic equation to calculate your displacement. As soon as it switches into that constant velocity section, where that rectangular shape is, that's where you have to calculate that as a separate displacement, then add it to the previous calculation.